So here we are, the next new PicoScope, and as you can see, a new look for Pico. You might well expect from us a new level of price or performance or both of those things. And we're going to show you as well that we have a new architecture here, a new architecture for an oscilloscope to give a new price point in broadband oscilloscopes. As you can see, we have 4 channels. We have power and control interfaces around all of those 4 channels. If I turn the unit around, then we can see on the back we have USB and LAN interfaces, and we have 12 volt DC input for power. Coming back round to the front, over here it says that this is a 5 gigahertz oscilloscope and that it is a 12-bit product, 12-bit ADCs. It also says that it's an SX RTO. So I'm Mark Ashcroft, and this is the PicoScope 9404 Sampler Extended Real-Time Oscilloscope. Now I hope you're all wondering how Pico is going to pack all of that sort of performance in such a neat little portable instrument like this. And I'm absolutely certain that those of you that are in any way familiar with the price of broadband oscilloscopes will be pondering as well how Pico can achieve all of that at a selling price of less than $15,000. Let's connect up and get some software running. And I'll also connect a pulse generator here to channel 1. I'm using the PG900, our fast step pulse generator there. So starting the software, this is PicoSample 4. It's a derivative of PicoSample 3. This is a software that we've been using for some time with our range of sampling oscilloscopes. PicoSample 4 derived directly from it. As you can see, we're already up and running, and if we auto scale it, we will shortly see our pulse train, and there we go. Up and running really quite smartly. Let me get some more connections made so that we can show you around the software. Let's turn the channels on and hit auto scale on those. Okay, there are 4 waveforms. Let's have a look around. I want to make sure that we've got touchscreen control on. Yes, we have, and therefore the last parameter control that I touch on the screen here will be enlarged for me, and that helps with some of the touch operation. Let's have a look around. What have we got here? We've got, first of all, the channel controls with their status displayed here, and above we have a complete summary, tabulated summary of the scalings and offsets of the channels and of the time-based control. Up here at the top, at top of the screen, we can see a summary of time-based settings. We're operating in real-time sampling mode, and you can see here are the waveforms being captured at quite a fast rate. Over here we have trigger, and in the trigger summary we've got a rather useful frequency counter here. This is indicating the trigger rate, the incoming trigger rate, which happens to be at the moment on channel 1. Looking slightly to the left here, these are a summary of the channels. Again, their scalings and their offset. If I turn off a couple of channels, you can see that I continue to get an indication of the waveform on those channels up in the status summary at the top here. Now that might be important because those waveforms might, for instance, be contributing to a maths waveform that we are displaying. Let's turn channel 1 back on and let's call up the display menu, and we will select dual graticule instead of 4. Let me call up another menu as well. I'm going to call up the acquire menu, and as you can see, I've got the versatility here to put up two menus up at the same time. This allows me to configure from the main menu controls at the bottom of the screen here. I can call up all the menus that I want for a particular application. The user interface is, if you like, user configurable. The screen is touch operable, so we can change our trigger channel. We can grab hold of the trigger level here, move it up and down. We can see the parameter control enlarged here. I can move trigger level using this control as well. Let's put that back to 0, and then we can increment it downwards, or we can choose to type in what minus 0.2. And you can do that with all of the parameter controls, whether in the menus or on the main control set at the bottom of the screen. Okay, let me next turn on vectors to join the dots, dot join if you prefer to call it that. And then we're going to start to ramp up our, whoops, wrong way, ramp up our time base. Now, at this point, I've come to the end of our real-time sampling range. We're now sampling at 500 megasamples per second. I've only got 50 samples across the screen, and my waveform isn't exactly full of detail. This is not a problem because the waveforms I have here are repetitive, so I can switch to random ETS, random equivalent time sampling, and my detail in waveform is fully restored. I can also at this point push up record length. Now running at 200 gigasamples per second and 20 kilosamples, 20,000 samples across the screen. Let's get some measurements on. With statistics, I want on channel 1, I want rise time, I want amplitude, peak-to-peak jitter and RMS jitter. And you may notice that as I've gone through the process of turning those measurements on, I've been getting an indication on the screen as to how those measurements have being made. Here, for instance, the RMS measurement is being made at this point across that particular trace width. Let's get us up to 2 nanoseconds per division. So now I'm running at 1 terasample per second, still 20,000 samples across the screen, and we can see that we have a positive RMS jitter of around 1.2 picosecond. So this is a very, very low jitter oscilloscope. We have 5 picoseconds peak to peak. We have 64 picoseconds of rise time on channel 1. That is coming out at a mean at the moment of 65.74 picoseconds. Well, a 5 gigahertz scope should have a rise time of around 70 picoseconds. So clearly, given that we're measuring the rise time of the scope and the rise time of the pulse generator there, we've got plenty of bandwidth to reveal our rise time. Let me put on channel 2 full time. Where are you? There we go. We'll also put on trace to trace. Let's have channel 1 to channel 2. That's rise to fall. And there we are. We start to see there the skew between channels. Actually, I can vary that at the generator here. So there we are. That's all put on 40 picoseconds of skew. If I wanted to see that skew, I still got some more time-based ranges to go here. So as I go to 200 picoseconds per division, you can clearly see now the skew between the two channels. If I go back to the PG900 generator, I can deskew them thus. But let's not look at the detail in that way. Let me take you back down to 2 nanoseconds per division, and let's put on a zoom. If we enable a zoom capability, you can see that we've opened up another graticule window at the bottom here, and if we slide this zoom box over our waveform here, let's just put that to a factor of 10 and set it to 50%. There's the detail of the crossover between our rising and our falling edges, our differential high-speed edge. I can also enable a second zoom, and what I'm going to do, I'm going to pull that one to be the same, 50%, and then I can apply a vertical scaling factor to this, and let me apply the window to channel 2. And if I move that box down the screen, there we can see that second zoom window, revealing now all the waveform detail at the overshoot of that negative edge. And we can see there that we're beginning to really benefit now from 12-bit A to D resolution, and we're seeing all the detail still without any steppiness in that waveform there. If we look back here, we've got rather a lot of measurements up. We can move over and see the scales again. This is the scaling of all the channels and the 2 zooms that are currently up. We could choose to minimize that box, in which case that becomes a scrolling list for us. The same, of course, applies to measures. These are a scrolling list of measures, which we can rescale as we had before. Let's clear away all these menus, and we'll even clear away the permanent controls. We'll minimize the measurements, and now we've cleared all our screen of everything but traces, and this we might use to present our results to an audience, of course. And if we happen to be doing that on a 4K display, we would see that the PicoSample 4 software uses the full native resolution and displays all the waveforms and all the detail on that 4K display. Finally, in this video, let's step back to that real-time sampling limit of 500 megasamples per second. We need to take a look inside the 9404 to really understand where that limitation comes from. So here we are. I've set up the camera so that we can take a little peek inside the unit. I'm not going to reveal everything to you, But as you can see here, right behind the inputs we have 5 gigahertz track and hold and high-speed trigger comparators behind each of the input channels there. We have trigger receivers down here, master sampling clock generation towards the center, and below our performance critical trigger to clock phase determination. A little set back from each channel, A to D drive amplifiers and the 4 500 megasample per second 12-bit 8 to D converters. Converted sample data routes back to this large format Kintex FPGA. That features Core SRAM, which we're using for our trace stores. The whole instrument is supported by this ARM processor back here, and then USB and LAN interfaces down to bottom right. If we take a look at a block diagram of the signal path in our SX-RTO, and if we colour the various elements on that path according to their relative cost, what we see is that the 5 gigahertz track and holds are relatively expensive. The rest either moderately expensive or relatively low cost for every function within the product. If we contrast that with the block diagram of the signal path of a typical 5 gigahertz real-time oscilloscope, first of all we'd see that behind the track and hold we would now have 10 to 40 gigasample per second A to D converters, more likely to be 8-bit or 10-bit rather than 12. But these are significantly expensive components. The very high data bandwidth that they produce has to be handled by really high-speed data path and high-speed memory, and that can be tremendously expensive. Hence the very red block in the top right there. And to that we must add switched gain amplifiers just before the track and holds and the trigger pickoffs. Those in themselves are relatively high cost. So overall the real-time oscilloscope package is quite significantly more expensive than the SX-RTO. Of course it is those 20 gigasample per second A to Ds that give the RTO a much higher speed or single event capture capability. However, those relatively high speed A to D converters and the very expensive memory bandwidth still doesn't get us all that we might need in a real-time oscilloscope. If we consider the narrowest pulse that a 5 gigahertz oscilloscope would be able to capture, that would be a 150 picosecond pulse or data interval. If we capture that at 20 gigasamples per second, we're just going to get 3 samples within that pulse, and the fidelity of its reproduction is rather lacking. Now in real-time mode, our sampler extended real-time oscilloscope will do a rather worse job. In this case we really don't have enough samples to capture that 150 picosecond pulse or data bit in single shot at all. We can capture slower transient events, but we will miss that 150 picosecond pulse. All broadband real-time oscilloscopes and the SX-RTO use random equivalent time sampling on repetitive waveforms or clock-related data eyes to increase the sampling density. So, the SX-RTO gives us a new affordable price point for the broadband oscilloscope. Our high-speed signals do need to be repetitive rather than transient, but when they are, the SX-RTO will resolve high bandwidth signals with 12-bit and 1 picosecond sample resolution. That's 150 samples in our example pulse. So that was the PicoScope 9404 SX-RTO, our sampler extended real-time oscilloscope. It does what it says on the can, and the can isn't that expensive. Thank you.